Okay, so Dirichlet or fixed boundary conditions are simple to employ, but what if we specify a derivative at the boundary? We term this the Neumann boundary condition, and physically it corresponds to, say, a flux or a flow at the boundary, where the flux is proportional to the derivative, day phi by day x, for example. So in other words, if we had a boundary and we had our grids on the interior here, essentially what we're saying is that there's actually a gradient that we need to account for at this boundary condition. So say material can flow in or flow out. So it may seem a little arbitrary or difficult to conceptualize, but we can incorporate it quite easily into our finite difference scheme by using virtual nodes. So essentially at the boundary we would have following grid points: phi 0j, phi 0, j plus 1, phi 1j, and phi 0, j minus 1. But now we would include a virtual node, and we'd call this phi minus 1 j. So these nodes are all connected. Alright, so for node 0j, that's this node, and using the central difference, the gradient can be approximated as day phi by day x is approximately equal to phi of 1j minus phi of minus 1j divided by 2 delta x. Rearranging this, we get that phi of minus 1j, which is our virtual node, is equal to phi ij that should be phi 1j minus 2 delta x multiplied by the gradient in the x direction. We substitute this back into our Laplace operator, we get that 2 phi 1j minus 2 delta x day phi by day x, that is our boundary condition, plus phi 0 j plus 1 plus phi 0 j minus 1 minus 4 times phi of 0 j. That's obviously set to 0. And note, because the boundary condition or boundary value is of phi are unknown, the dimensionality of the problem has increased because we have now had to incorporate the phi values at the boundary, which are unknown, but we can relate them through the gradient. Okay.